Thank you, everybody, for being in my talk.
Close to the microphone.
Well, the title of my presentation is this one, Pseudo dihedral angles in proteins providing an L description of the Ramachandran map. Those three people were my co-authors in this article. And actually, I'm doing a postdoc at École Polytechnique, but I'm also I have bonds with the University of Lorraine. And well, my presentation will be divided in these four steps. Well, for the first one, I will talk about a protein overview. As Therese and Simon already said, well, proteins are chains of amino acid residues. I'm considering here that there are 20 distinct amino acids that can comprise a protein. Here is the general structure of amino acid residue. We have one amino group, one carboxyl group, and one side chain. The side chain is what is differing all the 20 amino acid residues. And well, just to see quickly how two amino acid residues can make a bond to create a protein. Here we have two amino acid residues. The OH from the carboxyl group of one amino acid will interact with another H from the amino group to the next residue. They will combine. In this case here we have a dipeptide. It is a protein form comprised by two amino acid residues. And for each connection like this, we will get a molecule of water. Well, if we are saying that our protein has n amino acid residues, and then this kind of interaction will happen n times. And here, this central part of the protein, here in this talk, I will consider it as the backbone of the protein. And as I said before, the side chains, they are different in different amino acid residues. And then because that, I will not consider it in this part of the talk. And I will consider that my protein is mainly defined by the backbone. Well, here I have one protein molecule from the PDB. The PDB is a protein data bank. Here we can see that we have a kind of helix and two arrows. As Therese mentioned, the helix are the alpha helix and the arrows are the beta strands. They play a really big role in the in folded proteins. But just to see how we can convert this visualization to the other ones with the spheres and the bonds, well, here I am just using a different representation of this protein. But, well, here another one where I am just replacing or putting in the same structure this representation with spheres and bounds. And here just this representation, because this one is the one that I am dealing with. And in this case here, I will also talk about the local geometry. The local geometry, as I'm defining here, is the geometry defined in one residue and its neighbors. Here in this case, we have two residues, the residue I minus 1 and the residue I, and part of the residue I plus 1. All the atoms that are here, they are part of those residues. I am not considering, in this case here, as I mentioned, the side chains. And well, these two planes here, they are supposed to be a plane, I mean, at least in theory. And then all the atoms that belong to the same plane, they should be planar. And the dihedral angles, that is important, well, at least that defines the backbone, are the dihedral angles defined here, the omega angle between two consecutive C alpha atoms, the phi angle defined between two consecutive C atoms, and the psi angle defined by two consecutive n atoms. As Simon showed, we can see here that they are dihedral angles. Then they are defined, they are the angle between two planes. And also here we can see that we have these planar angles in the planes. Those angles are called bond angles. And we will also call the bond between the two atoms that are bonded by a covalent bond as bond lengths. And then this is the local geometry that I'm dealing with. Well, here we have this Ramachandran map. It was proposed, if I'm not mistaken, in the 60s. And here we can see a database that was collected from X-ray data. And they measured the angle phi and psi and put in one diagram like this. This region that we have, this alpha and beta, it's related to the regions that we can get in a backbone, the alpha helix and the beta strands. And one thing that we can see here is that, well, this is a flat representation, but the dihedral angles, they vary from minus 180 to 180. And then in some sense, it should be a kind of torus. It could be a kind of torus. But in this representation, we are getting it planar. And then we can see a kind of discontinuity in the region that defines the beta strands here. And then what's our goal? Our goal is to try to construct a new diagram, Ramachandran diagram, Ramachandran map, trying to avoid this discontinuity in the beta region. And to do that, we are taking into account the hydrogen atoms that are attached to the backbone. And the other goal is try to describe these phi and psi angles, dihedral angles, with respect to hydrogen distances. And then, well, for do that, let's just take a view here in one part of the backbone structure. This part is from the atom Ci-1 to Ci. Here I'm considering that the residue I is not the glycine and neither the proline, because in the case of proline, we don't have this HN atom bonded here. We will see one example later. And for the glycine, this atom H alpha, it will be replaced by a H alpha 2. They have, in some sense, the same position in the space, just a little variation. But for this purpose, I'm not considering that this part of the structure, I'm considering that this part of the structure, we don't have these two residues here. And then let's draw some planes, because as we already seen, and as Samuel said, the dihedral angles are defined, are the angle between two planes. And well, here we can see that we have three planes, and the goal here is try to define the dihedral angles in those three planes. Well, it's quite hard to see something like this with this view, but let's try to look to this problem with another perspective. And then I will rotate the structure, but looking from the place where we have the eye. And then it's the same structure, just rotated. And then in this structure here, almost planar, we can see something, or at least it's more reliable to say some relationship between the dihedral angles. And I can also do something even further, that is just project this structure in the plane, and then we can write that structure like this. And then here we have a kind of planar angles, and it's, well, we can say without many problems that the angle in orange can be written as the sum of the other three angles. Well, for this case here is just one example. I just assumed one value for the dihedral angle phi. Phi is the one in black. But we can see that maybe this representation, I mean the angle in orange as the sum of the other three angles, will not be always the case. Well, in these three, here I'm just presenting the definition of those angles that are colored in the upper part. The angle in orange here we can see is a dihedral angle defined like this, but in the point of view on the biomolecular structure, we must call this angle a pseudo dihedral angle, because this angle is not defined like this one here. We don't have one bond between all the atoms in sequence, and then because that should be called a pseudo dihedral angle. And this one is the orange one. The second one is the red one here, and the last one is the gray one, this angle between the two hydrogen atoms. What we can see that it's common in all those three angles is that they have the same rotation axis. I mean, the rotation axis of all these three angles is defined in the bound that connects the atoms N and C alpha, I. Okay, and here below I have just the definition, the formal definition of these angles. These angles is just something that is interesting to remark, that here for the angle mu and nu, I'm considering this superindex N because it's related to this Hn atom. It will not be the case for the proline because we don't have this atom. And well, just considering that structure, as I said at the beginning, that we were considering that the peptide plane is in fact planar. But if we go to the structures in the PDB, we will see that this is not the case. And then, well, in this case here is the one that I already shown, that this hydrogen atom is in the same plane of the C alpha I minus 1, the C alpha I, and the N atom that is behind the C atom here. But for those two cases here, I'm considering that there is a small variation on this angle. And we can see that even this small variation for this case here, it will change completely the description from the relationship between those angles. And then this is something that we should remark. Now here I'm showing the same structure, but considering that the residue I is the proline. In this case, we have a C delta attached to the N atom, and in this C delta atom, carbon delta atom, we have two hydrogen atoms attached to this atom. As our goal is to take in account just hydrogen atoms, well, we will do the same process. Here, again, we are defining planes, we are rotating the structure, and we are getting this planar representation of this structure. Here, well, we should again define this angle nu and mu again, but considering that I'm not, in this case, I don't have the Hn atom anymore, but instead of it, I have this H delta 3. But I just replaced the Hn for this H by this H delta 3. And we can see that the relationship between those angles, they can follow, well, it's similar, but this is something that we should investigate or even take in account. But well, in order to get those two representations in one formula, we generalize the definition. Then we have these three angles again, these three pseudo-dihedral angles again. But instead of N or delta, I'm considering that it's like a kappa, because it can represent any character that names a hydrogen in a protein. And well, for the alpha case, I'm considering the alpha 2 and the alpha as the Greek letter Rho. And well, here I have the general representation, and then we wrote a theorem in the paper that is describing this this relationship for phi that depends on those angles that I defined. Well, the theorem is like this. As the phi angle is just in this interval between minus 180 to 180, we need to define a kind of way to get the value that if we are summing two angles, we can go beyond this interval, and then this function f here will put this angle back to this interval. It's just something that it needed to be written like this. Okay, but we can see that the representation in this case is just a sum of angles, and then in some sense this angle lambda it is a kind of constant, and the one that is varying is the mu, and then with this formulation we have the angle phi written in function of the variation of the angle mu. Well, the same thing could be done for the phi psi angle. I will just skip it quickly because of lack of time. But then we also wrote a theorem that is similar to the previous one. I didn't mention it, but for proving this theorem, we use the polar properties of the complex numbers, and the proof was done for the general case. And well, we performed some experiments. For our experiments, we analyze NMR structures from the PDB. NMR is nuclear magnetic resonance structures. Our dataset specification, we have 226 protein structures. In the NMR data, we have more than one model available for each structure. We always considering the structure 1. And in the end, we have almost 29,000 quadruples of dihedral and pseudo dihedral angles, phi, psi, mu, and nu. With these angles, we perform, we plot these graphs and use this linear regression, and we can see that our fitting, it's with the results we can see that the fitting in some sense matches our theoretical description, because in our theoretical description we had a line, and here in this case we can see with the fitting that this is indeed the case. Well, just for this case here that we don't have 1 as the slope of this line here, but for the other ones we have. And we also get some estimatives for the lambda coefficient. And then, well, this is the Ramachandran map, the usual one. What we did, well, as we saw that we have a connection between the angles phi and psi with the eta and mu, we try to propose different Ramachandran maps. And here we can see in this central one here that this description that is eta against phi, we can see that the beta strand region, it's just concentrated in the center of this map. We don't have that discontinuity anymore. And well, and then this part I will just skip because I don't have much time, but this is how we can connect this application with the geometry distance problem. Here I have a dihedral angle, an unusual one. Well, we have this cosine law for a trihedral angle that describes the cosine of the dihedral angle with basis on the only planar angles. This is a mathematical description. We can use it in proteins, well, at least in the dihedral angles that we defined. And then we can just find a formula for describing the mu angle like this, based only on the distance between hydrogen atoms. And okay, and here what we have is quickly the angles phi and psi defined with relation of the hydrogen distances. And well, this is how we can use this representation to deal with long-range hydrogen distances, because we can convert those long-range distances to phi and psi. And then this is just the conclusions. That is something that I already said. And I already said that I would like to acknowledge my institutions, and thank you for your attention.